Welcome, I'm Professor Sever. Today we're going to discuss limits from the standpoint of review in Calculus 1. So here's an example where, again, we have 0 in the denominator if we were to investigate functional evaluation. First thing I want to do is factor out a 3 in the denominator, and then I notice I have a difference of squares. Now you may not say that's a difference of squares, but really 8 is 2 root 2 squared. So we have a difference of squares. I factor, and then I cancel. Functions that agree at all but one point, which is what gives us this equality. And remember, now I've also brought the 1/3 out. First step, 3 factors in the bottom. It comes out of the limit. It's in the denominator, so it stays in the denominator. Another way to say it is it comes out as a 1/3, because they're really factoring out a 1/3. And finally, this last step is a rational function which you can evaluate by plugging in. And notice, here's the final answer, and I rationalize the denominator to get this result. So here's an interesting problem. Again, 0 over 0 form. Well, let me rewrite it. So notice algebraically, sine of x over x squared is the sine of x over x all over x. And let's analyze this. Where does the denominator go? 0. Where does the numerator go? 1. That's enough to tell us the limit does not exist. So this is a D&E problem. You have not 0 over 0 form. That's always D&E. Now sometimes, technically, at this point of the course, really, you should go further and do what, you might say? Well, you need to investigate to see, does this go to positive infinity or negative infinity, or does it in fact stay as a D&E? And really, we should do a sign chart here, and we would see, using the sign chart, we would see the right-hand side of 0 goes to plus infinity, the left-hand side of 0 goes to minus infinity, so the limit as x goes to 0 from the left, which is minus infinity, is not the limit as x goes to 0 from the right, which is infinity. Therefore, the full limit does not exist. And you'll see I have the sign chart here, and the appropriate analysis conducted, which justifies the does not exist. Okay, here's another nice problem. This time I'm showing a variety of techniques, well, just 2 techniques. So we have a kind of a simple problem, 1 minus cosine x over sine x as x goes to 0. We're looking at that limit. Again, the denominator is 0, so we cannot evaluate by simple functional evaluation. So for my first technique, I just want to multiply by the conjugate of the numerator. And you might say, why? Well, the answer really is because it works. Okay? If it didn't work, we wouldn't do it. You would try it, and then it wouldn't bear a fruitful result, and therefore you would discard that as a technique. But you'll see this, in fact, works. So I multiply by the conjugate of the numerator, which is 1 plus cosine x. This, of course, gives us the difference of squares, which produces 1 minus cosine squared x in the numerator. I leave the denominator factored. Okay, why? Because we're hoping we can cancel. Now remember your trigonometry. What's 1 minus cosine squared x? That's sine squared x. So now I'll cancel the sine x in the bottom with one of the sine x's on top. So the sine x in the bottom will be removed, as you see here. You'll have 1 sine x remain in the numerator, which you see here. And now, can we evaluate this trigonometric function by plugging in? The answer is yes, because 1 plus cosine of 0 is 2. Sine of 0 is still 0. So we have 0 over 2, which is 0. So this is a problem where the 0 over 0 form, the answer came out to be 0. Now let's look at the same problem in a different way. This time I want to multiply by 1 over x over 1 over x. Remember, anything over itself is 1, and this original problem agrees with this problem. And now we multiply the 1 over x through the numerator. We multiply the 1 over x through to the denominator, producing this result. And then you see these are our 2 favored trigonometric limits. So the limit of the quotient is the quotient of the limits. So I have a quotient of the 2 limits, provided both limits exist and the limit of the denominator is not 0. So let's see. if we can do that. So I pass the limit to the numerator and to the denominator, which I have here. And let's look. We know this is the well-known result 0, and this work is valid if this limit in the denominator is not 0, which it isn't. We know this is our favored limit of 1. So the final answer using this technique is 0 over 1, which is 0. And we do have the same result as we should in both methods. So we have a rational function. We have a theorem that says if you're evaluating the limit of a rational function and the denominator goes to 0, but the numerator does not, you always have a d and e. That does not exist. Again, what really we should investigate is a sign chart of the original function so that we may make the determination whether the limit is truly does not exist, d and e, or plus or minus infinity. All right, the next case is, you probably can anticipate it now when you see that 1 minus cosine x in the light of this last example. We might think to multiply by the conjugate, which we do. Let's see if it works. Difference of squares again. We get 1 minus cosine squared, but we know from the last problem that's sine squared. I have the numerator still factored. Let's cancel a sine. Now this one still gives us something interesting, because now we still have 0 over 0 form. So what do? Well, this is where this is kind of a cool problem. Notice this x over sine x. Is that our favored limit? No, but it's the reciprocal of it. So if I reciprocate and put it in the denominator, it's equal to the original function. You need to work that out, but let's discuss it verbally. So let's prove it going from the right-hand side to the left. I'll show that this is equal to the original. So how do you divide? When you have a fraction over fraction, what do? You flip the denominator. That really means take the reciprocal of the denominator and multiply. So in slang terms, we say we flip the denominator and multiply. So the x would come up, which would give me x times 1 plus cosine x, which I have here. And it would just leave me with sine x in the denominator, which I have here. So these are equal. Now let's do the same thing that we did in the prior do the same thing we did 2 problems ago, where we pass the limit of the quotient into the numerator and denominator. A way to say that is the limit of the quotient is the quotient of the limits. We do that here. The limit goes to the numerator and denominator. And again, that method is justified if both limits exist and the limit of the denominator is not 0, which it is. Both happen. This is 2. The limit, the denominator goes to 1. So the final answer is 2 over 1, which is 2. So this is a nice technique where we had to kind of do 2 things. It wasn't simple enough to where we would apply one move or one maneuver and be done. We had to actually apply 2 maneuvers. And again, there are other ways we could have done this problem. Let's look at some more examples. So give an example of a function f and a function g such that the limit as x goes to 0, the limit as x goes to 0 of f is 0, and the limit as x goes to 0 of g of x is undefined, but the limit of the product exists. In fact, we saw an example of this a moment ago. The simple example is f of x is equal to x, and g of x is equal to 1 over x. So certainly the limit as x goes to 0 of 1 over x does not exist. The limit as x goes to 0 of x exists. And the product, of course, exists because the limit is 1. And we saw an example of this in a prior problem. This was an example of this. It wasn't at the value of 0 as indicated in that example, but it still had the same feature. This limit was 0. This limit was undefined, but the product existed and was 7/4. So we had even seen one example like this earlier in these notes. However, it wasn't at the value of a half. Okay, let's look at another one. Give an example of f and g, such the limit as x goes to 0 of f of x is 0. The limit as x goes to 0 of g of x is 0. So they both exist. They're both going to 0. But the limit of this ratio exists. All right, simple example, sine x over x, our favorite limit. Sine goes to 0 as x goes to 0, and as x goes to 0, x goes to 0. But the ratio sine x over x is our favored limit. We know that goes to 1. And this is reverse, so it's the same hypothesis. Both f and g go to 0 as x goes to 0. However, now the ratio doesn't exist. simple example would be let f of x equal x, let g of x equal x squared. And so you would get x over x squared, which cancels, which gives you 1 over x, which certainly doesn't exist at 0. I'm Professor Sever. Thank you for watching a review of limits.